Hey everybody. I wanted to give everybody a couple more examples of how to put a system into state space form. So I'm going to do two work through examples where I go from an image or a system diagram all the way through to getting that system put in state space form. So here we go. I think I'm actually going to do this one second. It's a little bit trickier. Let's do this one first. If you've been to office hours with me in this past week, this is probably the one that I had you do in my office hours. So just so that it's available to everybody else, let's work this one. So here I have three masses that are all connected in series with a spring in between each. We also have some forces being applied directly to each mass. All right. So I actually haven't given you enough information here. Let's say put this system into state space form, assuming the inputs are F1, F2, F3, and the outputs are X1, X2, X3. Okay? So I need to find the equations of motion for this system. And so to do so, I will draw the free body diagram of each mass on its own. All right? So let's start out with the free body diagram of mass 1. And it's important that you show the direction that you're assuming is the direction of positive displacement. So the direction of positive displacement is going to the right here for x1. Okay, so what I like to do to try to figure out the direction of forces is, in my mind, try to think about what would happen if I displaced this mass some amount in the direction of positive x1. So if I move this m1 to the right a little bit, this spring on the left-hand side is going to be in tension, and so it's going to pull back on this mass. So it's going to create a force that goes in this direction in the amount of K1, X1. Okay, this force is just an external force from the control engineer, so it does not depend on the state X1. But this second spring is a little bit more complicated. So when I have a spring that is between two elements or between two masses here, the force from that spring depends on basically the gap between these two objects. So the way that I like to think about this is to start out by pretending that x2 is not allowed to move. We're going to start out by pretending that this thing is a brick wall. The spring is just between the mass 1 and a brick wall. Okay, so if that were the case, if I moved m1 in the direction of positive x1 displacement, I'd be putting this spring into compression, which means it's going to push back on the block. So it's going to create a force that goes backwards like this in the amount of K2 times X1. Okay, now I put an open parentheses here because in all actuality, X2 could possibly be moving and it would not be a brick wall. So let's say that I've still, this spring is in compression, I've moved some amount in the X1 direction. If I were then allowed to have this endpoint move in the direction of positive x2, I like to try to think about whether that would increase the force in the spring or whether it would decrease the force in the spring. So it turns out if you move this endpoint to the right in some positive x2 direction, it will relieve the compression of that spring, and so it will reduce the amount of force in that spring. And so because it's reducing the force caused by the x1 displacement, we want to subtract x2. Okay? I do a very similar thought experiment for dampers that are between two masses, and it will work out very, very similar. So dampers always resist the movement of the block, so they always push against the direction of motion. And then you can work out the relative velocities the same way as I just did for the spring. So start out by assuming that the second degree of freedom is held constant, it doesn't change, and then determine whether releasing that degree of freedom would add or subtract from the initial force that you thought it would be. Okay, so let's leave this here, and let's do M2. Let's do M2 over here. M2 is connected to this same spring K2. So all I need to do is take this same quantity and apply the arrow in the opposite direction. So K2, x1 minus x2. Because by Newton's second law, we should have equal and opposite forces on either side of that spring. Okay, so the order, it stays x1 minus x2. We don't multiply it by a -1 or anything. All we do is change the direction of the arrow. On M1, it pushes to the left, and on M2, it pushes to the right. Okay, I'm going to add F2 here as our external force, and then I have this force by the spring K3. So again, if I hold X3 constant and I move M2 to the right, that would put this K3 spring in compression, so it's going to push back against M2 in the amount of K3 X2. But if I then allow X3 to move to the right, it will reduce this force. So this becomes, whoops, didn't mean to move my arrow. This becomes X3, X2 minus X3. That's my spring force. Okay, and then finally I have my mass 3, which has that external F3, and then the equal and opposite spring K3 force. So opposite meaning it pushes in this direction, equal meaning that it's still K3 x2 minus x3. All right, so those are my 3 free body diagrams. Now I need to go from free body diagrams to equations of motion, and I do that by finding the sum of the forces equals to mass times acceleration, and in this class, acceleration, we use the double dot form. So the acceleration of block M1 is x1 double dot. Okay, so on the left-hand side, I'll have M1 x1 double dot, and then I just need to sum my forces, assuming that pointing to the right is positive, because I've defined that when I set x1 to the right as positive. Okay, so F1 is going to be positive, and then these other 2 forces will be negative because they point to the left. Okay, now let's do M2. I should have M2 x2 double dot equals, whoops, I forgot to draw my direction that was positive. There we go. F2 plus K2 x1 minus x2 minus K3 x2 minus x3. Lastly, M3 x3 double dot equals F3 minus K3 x2 minus x3, because x3 goes to the right. All right, I have equations of motion. I'm going to collect these and then put them on my new page, and then we're going to rearrange them a little bit. I'm going to put that one there. Put that one there. Paste. Okay, so what I want to do before I go deciding out about state space and whatnot is I want to arrange these equations so that the x double dots are alone on the left-hand side, and then all the terms on the right-hand side are grouped by the x that they multiply. So let's see what that looks like. The first thing I'm going to do with this first equation, do 1, 2, 3 here. So the first thing I'm going to do for this first equation is I'm going to say m1 x1 double dot equals f1 minus k1 x1. I'm going to distribute this k2 term. And now I'm going to regroup so that I have a single constant multiplying x1. So I'll get m1 x1 double dot equals, I'm actually going to go ahead and move this f to the end as well. I'm going to do minus k1 minus k2 all times x1 plus k2 x2 plus f1. And then lastly, I'm just going to divide by this m1. So I'm going to take m1, 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 and then erase it on the left. Okay, so this is the version of the equation that will be most useful when I go to put this system in state space form. You'll see why later, but just trust me that rearranging things now is going to make the next step a little bit easier later. All right, let's do the same thing for the second equation. m2x2 double dot equals k2x1 minus k2x2 minus k3x2 plus k3x3 plus f2. I didn't do that right. No, I did. Okay. Let me double check. k2x1 minus k2x2 minus k3x2 plus k3. Okay, good. All right. So now I just need to divide by, nope, I need to group by terms and then divide by m2. So let's group by terms first. So I only have one x1, so we'll leave that k2x1. I have two x2 terms, so this should be minus k2 plus k3 all times x2. I have one x3 term and my f2. And then lastly, I need to divide by m2 on both sides. Okay, that's all ready to go. And let's do the last one. Minus k3x2 over m3 plus k3x3 over m3 plus f3 over m3. Okay, I'm even gonna maybe highlight these just to make them a little bit easier to pick out. All right, my next step in going to state space form is I need to figure out how many items are in my state vector. So I need to figure out the value of n. So how long is my state vector? Okay, so the process here is that we need to look at each variable in turn, x1, x2, and x3, figure out what is the highest order that that variable appears in these equations, and the lowest order. Okay, so for x1, the highest order is going to be this x1 double dot in this first equation. So the highest order is 2 because I have two derivatives. But then in these equations, I also have just a plain Jane x1 without any derivatives. So my lowest is 0. The same thing happens for x2. I have an x2 double dot in the second equation. I have an x2 plain Jane x2 in the equation itself. x3 double dot is in the third equation, and plain Jane x3 is on the right-hand side of that same equation, so 0. All right, the number of items in the x vector, n, is equal to the sum of the highest order minus the lowest order for each of these variables. So it'll be something like 2 minus 0 plus 2 minus 0 plus 2 minus 0 equals 6. So that means there are 6 items in my x vector. 1, 2, 3, 4, 5, 6. All right, the next thing I need to do is figure out what are those 6 items. Okay, so the procedure here is to go variable by variable and first input the lowest order of that variable and then continue adding higher and higher orders until we get to the second highest order for that variable. So for x1, I have just a plain Jane x1. Then I add the next highest order, x1 dot, but I do not include the highest order, which is x1 double dot. Then I'll do the same thing for x2, x2 dot. Same thing for x3, x3, x3 dot. All right. This is my state vector. Next thing I want to do is find the time derivative of the state vector. So I have x1 dot, x1 double dot, x2 dot, x2 double dot, x3 dot, x3 double dot. I can also at this point define my u vector, which is my inputs. My inputs were defined verbally in the problem statement. It says that the inputs are f1, f2, and f3. The outputs are x1, x2, and x3. So the way that we write that is u equals f1, f2, f3. Outputs y are x1, x2, and x3. All right. All that's left now is to write this in like the skeleton form of my state space equations. So my state equation is this x dot equals a x plus b u. And I'm going to go through and fill out the vectors that I know already. So x dot here will be x1 dot, x1 double dot, x2 dot, x2 double dot, x3 dot, x3 double dot. So x dot equals some matrix A times my state vector x, which is x1, x1 dot, x2, x2 dot, x3, x3 dot. Plus, I'm going to have to do b and u on the next line. I'm not actually really sure what shape b is going to take, but I do know what u is going to be. U is going to be f1, f2, f3. Okay, now we can figure out what is the size of a and b using our linear algebra rules. So when we multiply two matrices, if we have the row and the column of one matrix and the row and the column of another matrix, the inner dimensions must agree, and the outer dimensions tell us what the size of the resultant matrix will be. Okay, so for instance, if I have 1, 2, 3, 4, and I have 4 and 5, I have a 2 by 2 multiplied, so this is 2 rows by 2 columns, multiplied by 2 rows by 1 column. The inner dimensions are the same, so that means this is okay to be multiplied together. And the outer dimensions tell us the shape of the resulting matrix, which will be a 2 by 1. So I'll have 2 rows, 1 column. Okay, so this should result in this shape. Okay, so let's see what that means for our problem. So for our problem, we know that the x vector is 6 rows by 1 column. So for a to be multiplied by it, we know that the number of columns has to be equal to 6. But we don't know the number of rows. However, the result of these two matrices needs to be the same size as this matrix on the left-hand side of the equation, which is a 6 by 1. So if the result of this multiplication needs to be 6 by 1, this needs to be a 6, so that we get a 6 by 1. Okay, so A is a 6 by 6, and now we can do something similar for B times U. U is 3 rows by 1 column. So B, to multiply by this U vector, has to have a 3 right here so that the inner dimensions agree. And I need the result of this multiplication, again, to equal a 6 by 1. So this must be a 6. So that means B is 6 rows by 3 columns. So something like this. Something like that. Okay, so now we know the size of these matrices. Let's try to fill them in. And to do that, I'm going to need to, again, collect my equations of motion. So let's go get those again. Uh-oh. All right. Okay. So if we look on the left-hand side, we need the result of AX plus BU to equal X1 dot. But X1 dot is part of my state vector. So all I need to do is pick it out of my state vector. So I need to multiply 0 times X1 plus 1 times X1 dot plus 0 X2, 0 X2 dot, 0 X3, 0 X3 dot. There are also no F1s, F2s, or F3s because no F's appear over here. It's just X1 dot, so I just need to pick it out of the state vector. Now X1 double dot, in order to fill that out appropriately, we need AX plus BU to equal this equation, this first equation of motion. So let's look at everything that's multiplied by X1. That needs to go in this first slot. So that would be minus K1 minus K2 all over M1. We don't have any X1 dots in this equation, so that's going to be 0. We have stuff multiplied by X2 though. That's K2 over M1. No X2 dots, no X3s, no X3 dots. So 0, 0, 0. We do have a 1 over M1 multiplied by F1. So this needs to be 1 over M1, 0, 0. Okay, X2 dot is a state, so I need to put a 1 at the 1, 2, 3, 4th column. 2, 3, 4. There are no F1s, F2s, or F3s. Okay, X2 double dot. We need to look at this second equation of motion, X2 double dot. The first thing is multiplied by X1 is K2 over M2. No X1 dots, so 0 there. X2 is going to be minus K2 plus K3 over M2. No X2 dots. X3 is K3 over M2. And no X3 dots. And then I have a 1 over M2 times F2. So 0, 1 over M2, 0. Okay, X3 dot is a state. It's the penultimate state or the next to last state. So 1, 2, 3, 4, 5, 6. And then x3 double dot needs to result in this equation. So we have no x1s, no x1 dots. x2 is minus k3 over m3. No x2 dots. x3 is k3 over m3. And no x3 dots. Oopsies, I forgot to write my zeros for my x3 row. And then this last part is 1 over m3 times f3. Okay. That is my state equation of state space form. So I found x dot equals ax plus bu, but I now need to find y equals cx plus du. So again, what I'm going to do is fill in the vectors that I know. So y we determined earlier is this one, x1, x2, x3. Equals some matrix times our state vector, which we know, x1, x1 dot, x2, x2 dot, x3, x3 dot, plus some matrix D, not sure about it yet, times U, which is F1, F2, F3. All right, let's do our linear algebra again. Everything needs to result in a 3 by 1. This is a 6 by 1. This is a 3 by 1. So this C matrix needs to have a 6 here and a 3 here. So it has 3 rows, 6 columns. And then this one over here better be 3 there and a 3 there. So 3 by 3. Okay, it just so happens that our outputs are all members of our state vector. So I can just pick them out with 1s. So x1 is just 1 times x1 plus 0 times everything else. x2 is a 1 in the third column and a 0 elsewhere. And x3 is a 1 in the fifth column and 0 elsewhere. And that's it. There are no f's at all anywhere in this output vector. So this is just a matrix of zeros. All right. So this is your C matrix and this is your D matrix. And now you are in state space form. All right. I hope that helped a little bit. Now I'm going to do a little bit more challenging one. Let's go back up to that other problem that I had written out. This one. Let's do this one now. Okay, so I have this system. My input is going to be this forcing function f of t. My output is going to be both x1 and x2. Now this one is one of those challenging ones where we have a very strange connection of springs and dampers. So anytime we see this connection of or this series connections of springs and dampers, I want you to think that it's probably going to be best to put a 0 mass in between the series connection so that you can keep track of that extra state, and it'll make drawing your free body diagrams much easier. So what I'm going to do is I'm going to redraw this system as though there is a mass there, but I'll make sure to indicate that that mass is actually a 0 mass. So M1 stays the same. K2 stays the same, but now I'm going to put this extra mass here. I'll call it M3, and that will be between these connection points here. M2, this is X2, this is X1. All right. So now, oh, sorry, I needed to be very careful to indicate that M3 has actually 0 kilograms of mass, whereas we'll assume that M1 and M2 are non-zero. So now let's draw our free body diagrams of each mass. Okay, if I move M1 in the direction of positive x1 displacement, I need to give myself some more constants here. Okay, if I move in the positive x1 direction, this spring is going to pull back x1 or k1 x1. This damper is going to pull back with b1 x1 dot. If I pretend that m3 cannot move, if I move in the direction of x1, then this k2 spring is going to be put into compression, and it's going to push back on m1 with a value of k2 x1. But then if x3 is allowed to move, it will relieve the compression on that spring, and so I want to subtract it from my initial force. Don't forget your external force there. Okay, now I need to draw a free body diagram of M3. Try to squeeze that over here. Okay, I have an equal and opposite spring force. So I changed the arrow direction, but nothing else. And then if I move mass 3 in the direction of x3, and I pretend that x2 cannot move, then spring K3 is going to be put into compression. It's going to push back on M3 in the amount of K3 x3. But if then x2 is allowed to move, it will relieve some of the compression on that spring, so it will reduce how much force is built up in that spring. So I want to subtract x2. Very similar thing happens with this damper. I'll have b1 x3 dot minus x2 dot. It's the same logic as for the spring. It's just that it's velocities now instead of positions. Okay, and last but not least, we need the free body diagram of M2. And I'm going to need additional pages. There we go. M2. M2 just has this spring and this damper that are equal and opposite of the way they were drawn on M3. So this is going to be K3 x3 minus x2 and b1 x3 dot minus x2 dot. All right. Those are my free body diagrams. Now I need to find the equations of motion, so I need to do the sum of forces equals mass times acceleration for all three of these blocks. So I'll do m1 x1 double dot equals, oops, forgot to give the direction of positive displacement. Looks like F is the only thing that's positive, minus K1 x1 minus B1 x1 dot minus K2 x1 minus x3. All right, M3 x3 double dot equals K2 x1 minus x3 minus K3 x3 minus x2 minus B1 x3 dot minus x2 dot. And last but not least, M2 x2 double dot equals, K3 x3 minus x2 plus B1 x3 dot minus x2 dot. All right, just like I did before, I'm going to pull these equations of motion down below and do some rearranging. I also need to recognize that M3 is equal to 0. So specifically for this equation of motion, the sum of the forces will equal 0, only for that particular equation of motion. Okay, let's grab this equation. Let's grab this equation. And let's grab the last one. Okay, so just like I did before, ideally we would like the x1 double dot on the left-hand side all on its own, the x2 all on its own on the left, x2 double dot all on its own on the left. And then this middle equation, I'm actually going to solve for x3 dot and try to get rid of x3 dot everywhere else so that I can treat x3 dot as part of my derivative of my state vector. All right, so let's rearrange the same way I did last time. Minus k1 x1 minus b1 x1 dot minus k2 x1 plus k2 x3 plus f of t. I'm going to group by terms and then divide by m1. Minus k1 minus k2 over m1 x1 minus b1 x1 dot plus k2 x3 plus f of t. Oh, I still forgot to divide by m on all of those terms. That is a bummer. M1, M1, M1. I need a little more space here. There we go. Okay, fixed it. All right, next equation. All right, let's say 0 equals k2x1 minus k2x3 minus k3x3 plus k3x2 minus b1x3 dot plus b1x2 dot. And now I'm going to solve this equation for this term, or for x3 dot. So let's bring it over the left-hand side and then divide by b1. So I should get x3 dot equals, let's see, how many x1s do I have? I think I have only the one x1 term. So k2x1. Do I have any x2s? Got this one, and that's an x2 dot. And I need to divide by b1. Okay, so plus k3x2 over b1. So that's that term and that term. And then plus b1 over b1 x2 dot. And then my x3s. So minus k2 plus k3 over b1 x3. Whoops. Okay. Lastly is this last equation. So this last one, I want to take this x3 dot and I want to substitute in the equation above. So that'll be m2 x2 double dot equals k3x3 minus k3x2 plus b1 times k2 over b1 x1 plus k3 over b1 x2 plus x2 dot minus k2 plus k3 over b1 x3 minus b1 x2 dot. Okay, now I need to rearrange. So we'll have m2 x2 double dot equals, where are my x1 terms? Well, I see this x1, and that's the only x1 that I see. So we'll have k2 x1, because the b1 cancels out. All right, what's next are my x2 terms. So I see this one and this one. So again, the b1's going to cancel out here. So I should have minus k3x2 plus k3x2. So these terms actually cancel each other. Then I have an x2 dot here. So it'll be b1 x2 dot. But then I also have a minus b1 x2 dot. So this term and this term cancel each other. And then lastly, I have a k3 x3 minus k2 x3 plus k3 x3. Okay, so let's, oops, sorry, that's supposed to be k3x. Oh, that's all messed up. k3, uh-oh, wait, no. That was supposed to be there, I'm sorry. So plus k3x3. The b1's cancel out, so minus k2x3 minus k3x3. And again, I have another cancellation, k3x3 minus k3x3. So I should get x2 double dot equals k2x1 minus k2x3 all over m2. That was a lot of cancellations. All right. That was more cancellations than I was expecting, to be honest. Okay, now's the fun part. So now we need to collect these equations that are now very nicely organized. Oh, need another page. Collect this one, collect this one. Collect this one. And now I need to go through the rote steps of putting these in state space form. So first I need to figure out how big is x. So I have an x1, x2, x3. I need to find a highest order and the lowest. Highest x1 is double dot. I do have an x1 on its lonesome. I have x2 double dot and an x2 on its lonesome. I have an x3 dot, but no double dot, and an x3 on its lonesome. So n here should be 2 minus 0 plus 2 minus 0 plus 1 minus 0. So n should be equal to 5. Let's figure out what goes in x. Start with x1. I go x1, x1 dot, x2, x2 dot, x3. I do not include x3 dot because that would be the highest order. Next, I have x dot equals x1 dot, x1 double dot, x2 dot, x2 double dot, x3 dot. Hey.
Can I ask you a quick question?
Yeah, sure.
Awesome. I think I just sent you an email about it, but it was just a question.
Okay, so that's x and x dot. Y, we know from the problem statement, let's go back up, said the output is x1 and x2, and the input is f of t. So this is x1, x2, input is just f of t. So it's a scalar. Same thing as last time, I'm going to put this in my skeleton form here. X dot equals a times x plus b times u. So you have x1 dot x1 double dot x2 dot x2 double dot x3 dot equals some matrix. Hint, it's going to be 5 by 5 because it's n by n. x1, x1 dot x2, x2 dot x3 plus something times u, which is just f of t. And we need the result of this multiplication to be a 6 by 1, so b must be a 6 by 1. Sorry, not 6 by 1, 5 by 1. All right, now let's go back to our equations. Let's grab them again. All right, x1 dot is just a state, so it's 0, 1, 0, 0, 0. x1 double dot, we need to look at our equation of motion. So x1 multiplied is minus k1 minus k2 over m1. x1 dot is minus b1 over m1. We have no x2, no x2 dot. x3 is k2 over m1. Oops, sorry. There's 0f in the x1 dot equation. There is a 1 over m1 in this second row. All right, my x2 dot is just a state, so that's 0, 0, 0, 1, 0. 0f's over there. x2 double dot is this last equation here. So I have k2 over m2. No x1 dot. No x2. No x2 dot. x3 is minus k2 over m2. No forces on there. And lastly, this last equation of motion. So k2 over b1 times x1. No x1 dots. x2 is k3 over b1. x2 dot is just 1. And x3 is minus k2 plus k3 over b1. And 0 f's. So that's x dot equals ax plus bu. And then lastly, we need to do y equals cx plus du. So y is x1, x2 equals something times x plus something times u and this needs to result in a 2 by 1. So this is a 5 by 1. So this better be a 2 by 5. 2 rows, 5 columns. And this is a 1 by 1. So this better be a 2 by 1. Okay, x1 is just a state. It's 1. x2 is just a state. That's it. These are zeros. So this is C, this is D. And you're done. Okay, so long process. Really, it's just about memorizing the steps and then chugging through the procedure meticulously. And that's it. If you have any questions, feel free to reach out. I will try to post these notes in addition to this video.